Hey guys, Nick here, and today we're going to take a look at center of mass and how you calculate where an object or set of objects' center of mass is. Now this will be a rather short video. Mostly we're going to use this as a tool during the next video, which is torque. However, this is a subject by itself, so I'm going to cover it in its own video here. Now, basic idea of center of mass is it's going to give you the average location of an object's mass if the object is spread out. So if you have a point mass, obviously all of its mass is located at the same place. But if you have a more extended object, like maybe a ruler or a boomerang, the mass is going to be spread around a little bit, and this quantity is going to give you more or less the average location of the mass of the object. Now, as I mentioned, this is useful for a couple things. By itself, it doesn't really mean anything. The first thing is going to be that the weight force acts at the center of mass. Now, up until now, we haven't really cared about where forces act. We just care about how strong they are. But when we consider the next video, like I mentioned, which is going to be torque, torque is going to matter where force is pushing, because depending on where a force pushes, it may or may not cause an object to start trying to turn. So we're going to use center of mass in our torque videos just a little bit. And then the second thing, which is sort of in problems by itself, for example, those not involving torque is what I mean. Objects rotate around their center of mass when they're tossed into the air. So if you've ever seen a hammer tossed into the air, it doesn't spin around this geometrical center here. Instead, it kind of spins around that point, so the whole handle moves around this point. And that's because the center of mass of the hammer is concentrated towards the heavy head of the hammer. But again, the main way you're going to use it is in the torque problems. Okay, so quick definition of center of mass. We're going to start with in one dimension. So objects that are only distributed along the x direction. So an example of this would be, let's say here's our x-axis. Let's say here's x equals 0. Here's x equals 1 meter, 2 meter, 3 meters. And let's say I have a 2 kilogram mass here and a 3 kilogram mass out at x equals 3. And the question might be, where is the center of mass located for these guys? So again, that's going to be like the more or less the average location of the mass. So it's going to be somewhere in here, probably a little bit closer towards the 3, because the 3 is slightly heavier. And here's the formula that you'll use to calculate it. So the recipe is you're going to add up the mass of an object, so 2, and I'll write the general formula later, by the way, because it's pretty confusing notation. You're going to take the mass of the first object times its x location, and then you're going to add on the mass of the second object times its location in meters. And if there were a third mass, let's say, actually for the sake of this example, let's say out at 4, there was an 8 kilogram mass. You would continue adding on the mass of the object times the location of the object along the x-axis. So again, the mass times its location. And then at the very end, you're going to divide by this total mass, so the 2 plus 3 plus 8. And again, this is total mass, and this is mass of each object times location, and you're gonna add that up. I'll explain the symbol in a second. You're gonna add that up for each of the objects. Okay, and if you go out and compute this, let's see, we have 2 plus 9 plus 32 divided by 13. And if I punch that in, it seems I've picked unlucky numbers, 3.31. And sometimes you'll see it written as x bar. Bar refers to average. Okay, now I mentioned that there's a formula for this, and the formula is a little bit ugly, so I'll explain what it means and like point to what each thing was in our problem. So sometimes you'll see this formula unfortunately written as this. So this symbol is called capital sigma, and it's read sum. And you're going to add up for each object to however many objects there are, the mass of the object times the location of the object. And again, this symbol means you add up mass for object 1 times position of object 1, and then you add that on to the mass of object 2 times the position of object 2, and then you add on to however many objects there are. And at the very end, you divide by the total mass. Now, the total mass is the sum of the masses of each object, and you just add up however many there are. So again, in our example, that was m1 plus m2 plus m3, and the numerator in our example was m1 times x1 plus m2 times x2, and we had a third object plus m3 times x3. Sorry for the squeezing, otherwise I'll hit the scroll bar. Okay, so again, this is the formula you'll see on your equation sheet, obviously with the I that I missed boxed in. But in practice, this is what it means. All right, let's do another quick example just with point masses to get warmed up about it. Let's say here at x equals, let's make this 0. Let's say we have an object 4 kilograms over at 2 meters. And then let's say we have an 8 kilogram object over at -2 meters. So let's apply our general rule, which is to get the average x, we're going to add up mass times position. And again, it's okay that position is -2. If we get an average center of mass location of -1, that's fine. It just means it's to the left of what we called 0. Then we're going to add on the mass of the second object times its position. And then at the very end, we divide by, remember, the sum of all the masses, the total mass. So in this case, it's 8 plus 4. Let's see, 8 times -2 is -16, plus 8. So this is -8/12, which is -2/3 meters. So that's the location in the center of mass. And like I said, it's okay that the number you get out is negative. It just means it's to the left of whatever you called 0. Okay. Now, the common kind of problem that you're going to get involves not these little point masses, but some extended objects too. So, as a motivating example, let's say I had a meter stick. And at the very end, I attached a weight with mass 3 kilograms, and the mass of the meter stick is 1 kilogram. A question might be, where is the center of mass of this system if I call this x equals 0 right here? Okay, now what you'd run into is this issue of, oh crap, he told me how to do it when the mass is located at a specific place, but this meter stick is spread out. Should I use the left end as my x coordinate for it? Should I use the right end? Should I use the middle? And it turns out that the result is, and I don't know if this really warrants Galaxy Pen overall, but for the purposes of these problems, it does warrant a Galaxy Pen. The trick is, or the rule is rather, that if you have an extended object like a meter stick, you're allowed to pretend it's located at its center. Oops. And technically, it's at its center of mass. However, usually in these problems that you're being given, you're told the object is a uniform density. It's not heavier on one end versus the other. So the center of mass will be located in the geometrical center of the object. However, if they tell you, oh, this meter stick is wacky, its center of mass is actually here, then that's okay. You just pretend it's a 1 kilogram mass placed at wherever you're told it is. But in this problem, since we're not really told otherwise, I suppose I should have told you at the beginning, that this is a uniform meter stick, we're allowed to pretend that this whole extended meter stick is a single point mass located at half of a meter, right? Because the whole meter stick is 1. So here we are at 50 centimeters. So with that information, it'll be pretty straightforward to calculate where the center of mass is. Just like before, we multiply the mass of the object, so for the meter stick it's 1, times the location of the object. And again, for the meter stick, we're allowed to pretend it's all located at 0.5 meters in the center. So we're allowed to pretend the entire long meter stick is just all bunched up at that point. And again, it's 0.5 and not 1 because here's 1 over here, and we're pretending it's all at the center. Okay, then I add on position times location, or sorry, mass times location for this giant weight that I've attached to the end. And then at the end, I still divide by the total mass of all the guys involved. So the numerator, let's see, this is 0.5, this is 3. 3.5 over 4. And this is going to be a pretty ugly number. Let's see. 0.875. So average mass is more or less here. Sorry, center of mass is more or less here. Perfect. Okay, let's go on to a 2D example. Now, the only modification to the process for 2D is it turns out you can compute the x and y center of masses separately. Now let's get a motivating example here. Okay, here's my x-axis, y-axis. I'm going to put one mass here and another mass here. I'm going to call this one 6 kilograms and this one 4 kilograms. So what you're allowed to do is, beforehand, we were just doing the mass of each object times its x location. And you're still going to do that to find the x location, so where left or right is the center of mass for this system. You're just going to basically ignore the fact that these things are at different y coordinates. You're just going to care about their x coordinates only. So to find the x center of mass, we're going to do, as usual, the mass of the first object times, and again here you only use its x location. You ignore the fact that it's at y equals 2. All you care about is at x equals 1, and you move on. Now we're going to add on the mass of the next object times its x location, again completely ignoring the fact that it's at a different y position than the first one. So this one is located at x equals 2. Okay, and then just like before, you're going to divide by the total mass. Oops, sorry, 4 plus 6. Let's see, this is 4 plus 12 over 10, and if you punch this into a calculator, you're going to get it's 1.6. And again, this is the x location. We haven't found where it is along the y direction yet. And as you might have guessed, for the y direction, all you do is, instead of using the x coordinate of object 1 and the x coordinate of object 2, all you do is you do their masses times their y coordinates, completely ignoring their x coordinates. So for this example here, we would have the 4 kilogram mass times its y coordinate, which is 2, plus the mass of this object, 6, times its y coordinate, completely ignoring its x coordinate. And it's at y equals 1. And just like before, you're going to divide by the total mass, so 4 plus 6. Let's see, so this is 8 plus 6 over 10, which is 1.4. And again, this is the location of the center of mass vertically. So this is the y coordinate of the center of mass. So your full answer for this problem would be that the center of mass is located at x equals 1.6 meters, comma, y equals 1.4 meters. And if you want, you could give that as like an xy coordinate pair. So on our graph, that would be somewhere like here, over at 1.6 and up at 1.4, which is more or less what we expect. It's vaguely in between the two objects. Great. Okay, one more thing to point out here before I go on to one of the last examples is that an object center of mass, and I will write this in Galaxy Pen, an object center of mass doesn't have to be on the physical material of the object. This is just in Galaxy Pen because it's a classic trick question. One notable example is a boomerang. The average y location, as you make the boomerang a particular size, the average location in the center of mass, it might start here if you have a short boomerang, but for longer boomerangs, the center of mass will actually be out in the middle of this void right here, and that is totally okay. It's sort of like how if you look at these examples up here, for two masses, the center of mass wasn't on where the mass was at all. And the same goes even if it's just one extended object, which really is a sum of a lot of little molecules if you want. So this is totally okay. And don't be surprised if you get that a center of mass for an object is outside the object. It's totally okay. Okay, we're going to do one more example here that I thought was an interesting trick question that one of my professors gave. It's going to be the case of 3 stacked bricks. Oops. 3 identical bricks. And each brick is going to be of length L, mass M. And this distance right here is going to be 1/4 of L, and same with this one right here, L over 4. And again, all these bricks are the same mass and length. And the question is going to be, and again, this is a little tricky of an example, the question is going to be where is the x coordinate, so we're not going to care about vertically where it is, of the center of mass. Okay, so just like before, we're going to attack it by trying to do the mass of each brick times the x-coordinate of its little center of mass. Remember, these bricks are spread out, but we're allowed to pretend that they're all located as points at their centers here. Okay? So if we try to start writing our equation, we're going to write in the mass of brick 1, which is m, times the location of its center of mass. Again, condensing the extended object down to pretending it's a point at its center, sort of like how we did for the meter stick. So let's see, where is this x located? Well, the brick is length L in total, and this is halfway through the brick. So this distance should be L over 2, right? Half of the length of the brick. So the first guy is going to be located at x equals L over 2. Okay, what about the second guy? All right, he still has mass m, and now we need to multiply by his x-coordinate. Well, let's see. I kind of did a bad drawing here. X-coordinate's going to be like somewhere vaguely over here. Let's see how we can find the location of this x. Again, it's going to be, one thing that we do know is it's halfway in the brick. So it's L over 2 away from this left edge of the brick. And where's the left edge of the brick? It's L over 4 away from 0. So in total, you have 1/4 L plus 1/2 L, which means that this x is located at 3/4 L. Perfect. And now let's tackle the last brick. So again, we're going to add on his mass times his location of his little x. Now let's see, what location along the left to right axis is that x at? Well, it's L over 2 away from that edge, and that edge is L over 4 and another L over 4, so 1/2 L away from 0. So in total, it's L over 2 over to get to the start of this brick, and then the x is another L over 2 over to the right from that. So in total, it's just L. That's the location of this x. Okay, and then again, we're going to divide by the total mass of the object. So here we have 3 objects of mass m. M plus m plus m is 3m. Okay, now I'm allowed to cancel the m from everything in the numerator and the m in the denominator. If you want, you could factor out m in front and write it like as m parentheses times the other stuff. So the m's all cancel. Okay, and if I want, I can factor out the l's. Right, so I'm going to basically rip them back outside. Okay, and now all there is to do is to figure out what this number is. So we're going to need to go to least common denominators here. So we're going to convert 1/2 into 2/4. And then 1 is 4/4. Let's see, we have 2 plus 3 plus 4, and they're all over 4, so I'm allowed to add the numbers. Let's see, 2 plus 3 is 5, plus 4 is 9. Okay, and then, let's see, 9/4 divided by 3, that cancels one of the 3's in the 9. So I get that the answer is that the center of mass is located at 3/4 times L, which sort of looks reasonable, right? It's somewhere generally like over here, more or less in the center of where the bricks are placed left to right. Okay, excellent, guys. Like I said, this video is more so standalone, but it'll be really useful next time when we take a look at twerks. So I'll see you there.